This is Anagalactic bringing you another science presentation. We're studying astronomy. Often it is called, or I've heard it called, the queen of sciences. That's very kind. I agree, because wisdom is styled as a female. You can see that these are numbers. You may recognize them, and I'd like to begin by explaining why we're looking at numbers when we're actually studying astrophysics. Well, it's because of the word physics. It has the word mathematics in it, and mathematics has numbers in it. So we're very concerned with numbers, going beyond add and its complement subtract as we're taught, and going beyond multiply and divide, which we think we understand. But now, as I've said, just to introduce our topic of numbers, of what we're forced to do with numbers when we reach the edge. It's a very interesting concept, this edge, and you certainly can call to mind at least one word that describes the edge that is baffling to us. We call it infinity. This is a spatial concept, but it does extend to time as well. In certain extrapolations on the future and the past, we wonder if time is infinite as well. In some sense, either as being continuous, which is a key word here with numbers, but we're talking about both time and space in a way that Albert Einstein has taught us are intimately related, and we use numbers to explore this relationship. So it could become critical to understand what your numbers are at some point. The relationship between numbers and geometry is critical to us because we're using geometry to explore the universe. Astronomy, because of its concern with geometry, obviously the flights of the planets are geometric. No matter what you want to philosophize, numbers don't hold a candle to the flight of the moon around the Earth, or the flight of the Earth around the sun, or the Earth turning on its axis. And in fact, as a scientist shared with me the other day in a cafe, he pointed out to me that the sun is rotating as well. He had a beautiful photograph to show me of that, because that's quite true. The sun rotates, and the way you notice that is the path of the solar wind, which can be measured because it pulses with flares. Well, it can be measured anyway, but that makes it rather dramatic if you can get a photograph of it. Well, it's remarkable what we can get photographs of, but the point is, the solar system is purely understood, I'm safe in saying this, geometrically. But then there come the numbers. The numbers were certainly necessary to Kepler, and those numbers have been with astronomers ever since. But something happened a century ago that changed everything. We started to approach the edge. That is, the outer edge of the universe. The CMBR is direct evidence of an edge, and what is construed with some cosmological extrapolations, but the origin of the universe has been contemplated, obviously. Well, men have been contemplating the origin of the universe for a long time, but not with the level of penetration that began a century ago. Because numbers are so useful. Astrophysics is numbers. That's the difference. Because astronomy is not. Despite what I said, it's because they're so closely allied. In fact, it was proved in my lifetime that the numbers that we use are identical with a geometric object called the line. Now, you may have already known that or thought that you knew it, but it's different when it's proved. That's actually quite significant, and people sat up and took notice. It was J H Conway who proved that, but he's not remembered for that. So we begin today by looking at the numbers that John Horton Conway discovered, which are right there. Those are the surreal numbers. In an abbreviated diagram, which I'll now explain, you'll notice that it begins at the bottom. And although it's not scrolled very well, that's a 1 and a -1. Let me bring that into view here. There. So, well, where does it begin? Let's get the whole thing here. 0. Okay, 0 is already a very special number, is it not? Yes, but we're going to complete talking about this tree here. This is called a tree. You'll notice that it's a binary tree. That's a computer geek term, but I trust that, if you never heard of that term, you can guess what it means since you're looking at one. It's a tree that splits in 2 and then in 2 again. These are powers of 2. So the first line above 0 has 2 elements. That number 2 characterizes the binary system. These numbers that you're looking at have names, of course. The bottom one is 0. What's the second one? You could give that, if it's just one number, is that just one number or is it 2? Well, it's the same number. It's a 1. We have a different term for that, though. That's either the numeral or the digit, but basically with or without a plus or minus sign, because the 1 could be drawn with a +1. That is a plus sign in front of it. Just, well, the -1 got a minus sign, so why? Because it's conventional to leave it out. But it does raise an interesting aspect about the first number after 0. These are, of course, the whole counting numbers. That's only line 2. What this is the beginning of the definition, the visualization of the definition of a number. And John Horton Conway, actually a few decades before he died, discovered the definition of a number that now is accepted. And that, you might think, well, didn't we always know what a number was? Yes and no. And it's a very strange thing to be able to say, but I've gotten used to it. That is actually superpositional logic. That's a superpositional answer. And superposition has to do with hierarchy. It's when it's not yes or no, but it's still logical. Because of the possibility of it being yes and no. And that's a characteristic of how you have to explain your queer answer when someone asks, for instance, are numbers real? Well, yes and no. But you see, that's against binary logic. It's either true or false. Well, not in superpositional logic. It's either true or false if it's one or the other. And that is true. That's called machine logic. That's 0, 1. But logic as we know it permits a certain special situation where it's yes and no. And that's because of if you look, as I have, it's because it's hierarchical. It's because it could be yes, depending on what you mean. And oh my God, now we get into philosophy. What do you mean? Are numbers real or not? Well, there is a whole ball of worms being explored right now about what's real or not, because it's mathematically significant. So to understand what a number is turns out to be critical to understanding how mathematics teaches us about the universe. So to get going here, these are the surreal numbers. And for those of you who love art, or you've heard of Salvador Dali, who is certainly one of the greatest artists who's ever lived, I think he is the greatest, but I'm not going to write a journal entry about it. Well, John Horton Conway is one of my heroes, as I think you can tell. 3 years ago, he died of the COVID virus, and he's well missed. He was only in his early 60s, if I recall correctly. And he's the one who discovered the definition of a number. So this graph is highly significant, and I'm going to show you what it means. And nobody can explain something like this exactly the same way as someone else might explain it, because this is extremely, oh, I think you can see it's extremely deep. In fact, let me just reduce this a little so you can see a little more. That shows you where it's from. This is from the Illinois edu. That would be, of course, a university. This bottom number, we all know, that's the beginning of the number system. It's the center of the number system. If you are willing to go out on a limb and say that, you are correct. 0 is the beginning of the number system, but the answer is yes or no. And I'll tell you why. It's because 0 is the beginning of a number system. I discovered a second way to begin a number system that does not begin with 0. I hope your mind is jumping ahead, or if you've heard some of my recent lectures, you know why I say that knowingly. But this is correct, but it's only correct, technically, if you add an adjective. In other words, to say that 0 is the beginning of the number system can be true depending on what you mean by number system. Now, we think there's only one. There's a reason for that. There is only one. But then that changed in 2022. I discovered, and this is the strangest thing I've ever been able to say in my life, but I discovered that actually the universe begins differently. And this actually comes down to the fact that we use the word uni to describe the verse. The uni verse, that uni does not mean 0. Uni does not mean 0. It means 1. And that number is on this graph, but it is definitely not 0. And the reason I'm emphasizing that, I always assume that you have not seen my previous lectures, either the past 3 or the past 6 or the past dozen. I would recommend all the way back through November, but you can go all the way back to June and see all 300 lectures. But science is nothing if not the art of summarization. That actually is a function of understanding. You have to be able to simplify your knowledge. Simplify it. If it's too complicated, you haven't understood it. I think you can see that's a pretty good description of physics for the past 70 to 100 years. At the cutting edge. You always have to add that. At the cutting edge. That would be astrophysics. But there are 2 cutting edges. The other one is quantum mechanics. And everyone who knows anything about mathematics, not meaning to talk down to anybody, because I'll complete the sentence if you're not sure what I'm leading up to. But the universe is one thing. The question is, does it use a number system based on 0? Now, you and I were taught that that's tautologically true. And from a certain aspect, that's undeniable. The number system that we use is definitely a 0-based system. You can see it in this diagram. because this is officially accepted by science now. I haven't seen anybody who questions the fact he didn't get a Nobel Prize, and he can't now because he's dead, and the Nobel Prize in physics or mathematics, which is included in that prize category, is only and by the way, there's another prize that's much more prized in mathematics. Actually, more than one. It's not the Nobel Prize. Mathematics has its own little gaming system for the prizes, which is all very fascinating. But everybody accepts that the number system begins at 0, and John proved it. But what I proved is that in order to be technically correct, that John's answer is correct, you have to add another word to what he discovered. Did he discover the definition of a number? The answer is yes and no. And I'm going to give you both sides of it to break. That's called a paradox, by the way. But superpositional logic comes to the rescue, but then you have to do some work. You have to study the structure of the yes and the no. And if you don't do both, you won't get anything right. Which means you have to learn to split your mind. Because the answer at this level, at the cutting edge, is always going to be superpositional. You might ask why. Can I prove that? You might ask why, and you might demand that I prove it. We're going to come about that in this lecture from the other direction by looking at numbers, and by the end of this lecture, you'll have the answer. But the word that you have to add is linear. This is a linear system. That's why it has 0. It's because it's linear. You can say it the other way around. Because it's linear, that is, it is a geometric object called the line. When we were taught the number line, nobody bothered to tell us that that's redundant. That when you say number, you say line. Now, I've actually found out that even what I just said is not true. Because when you say number, you might be saying line. But what makes the difference is the operator. It's the operator for the object. And this is, I've never heard anybody say this, but I'm going to tell it to you point blank. The line is defined on its operator. And the operator for the geometric object called the line is add, and nothing else. Well, you might ask, well, where do we get multiply and divide from? And didn't you leave out subtraction altogether? No, all 4 are still there. They're still the basic operators, although we actually have more operators now. Calculus is an operator. I don't know if you knew that. And there are other operations such as sine, cosine extraction, which is a dual number. That could actually be called an operator. The sine, cosine, the CIS operator. It's just that it's strange because it produces 2 numbers that are always together. Sine and cosine always occur together. They're both less than 1 by definition. So operator is an interesting term. We were taught 4 operators, were we not? I'm going to show you there are only 2. I think you already know that though, but this needs to be spelled out. Because of 0 and its position in the number system, it's always at the center. And you can see the center in this binary tree. It splits from plus to minus. Why? It's because of a 180-degree orientation on 0. That's the definition of a straight line. It has a specific orientation which is called opposite, but that has a geometric significance. It's 180 degrees, right? That's measuring on a circle, but that is significant. It certainly isn't a circle that's being described, it's a straight line. That's why you begin at 0, is to get linear separation. That's why it's called linear. That's why our algebra is called linear algebra. It's based on the jump from 0 to 1, which is defined as spatial. It's spatial. And that's all it is. And that's why 2 is so easy to understand. Once you realize that it's a specific distance, a distance of 1, that is a distance from 0 to 1. Well, that's the same distance as 1 to 2. And that's where we get 2 from. It's 2 1s. And 3 is 3 1s. But it goes the other direction too, doesn't it? That took a long time to discover. It's strange, and it makes you think that the ancients were very primitive. Well, they were in one sense. They didn't really understand the number line yet. In fact, 0 had not been discovered at the time of the Greeks. You must say that they must have had a concept of it, because, but actually, I mean, the historians agree on this, that they really didn't. Well, they did. You can't say they didn't, but they didn't care. They were after the shapes and the areas. And that's why the squared term is geometric. It's a square. Well, here we begin with a definition of the numbers that are used to describe the universe. They've been very useful and miraculous. Numbers, there's nothing wrong with the linear numbers. The linear numbers are the greatest thing. I mean, technology. I can't even imagine not having electricity. I've tried to imagine, and you go out in the woods and spend a week, because you're not going to have electricity out there. By the 4th or 5th day, you want to come back to your refrigerator, your heater, you want to get in your car. Well, that's all technology, which comes from linear algebra. So in no way am I saying that linear numbers are bad. Of course, they're the opposite of bad. But is there something better? The universe says yes. And it's very simple. You don't need to begin with 0. But if you don't begin with 0, you can't use a line. The line has add as its property. And that's what this describes, is the property of the line in terms of its numbers. It makes this tree. And this is the first ever visual definition of what is a number. It's a binary tree that begins with a split on plus and minus 1. That is extraordinarily significant, and in fact, John, who is treating this as a game, believe it or not, and his book is actually about gaming theory. In other words, he accidentally, while goofing around with games, figured out what nobody has ever been able. This absolutely goes past Cantor, Dedekind. It goes back past von Neumann. He got it. Everybody admits it. That's kind of rare. I mean, when you tell everybody in the mathematics community and everybody who uses numbers is that they never really knew what a number was until John told them, that can ruffle some feathers. Well, it didn't. And I checked it out. I had to, finally. Because they're called the Surreal Numbers. And I'm a great fan of Salvador Dali. I hated numbers because I can't do arithmetic very well. It's not even mathematics or algebra, which I actually do well. But arithmetic, I am retarded. Well, I like to say dyslexic. Actually, I should never... I do because I hate myself, I guess. Well, no, but there's a trauma, you can tell. I mean, I call myself a retard. That's not very bright. Well, because, yeah. I mean, I just proved it right there. I still am. But you shouldn't say that because it's not true. You're dyslexic or, it's genetic. You can blame God or the angels, but it's not your fault if you're like me. And I'm teaching you about numbers, but I can't really do fractions very well. Well, I am actually getting to that. I made a hideous error in my previous lecture. Well, the one before one of the two previous lectures. And I was so traumatized because I tried to fix it. I tried to edit, and my computer crashed. I mean, it's just a nightmare. When it rains, it pours. And I almost cried because I spent like 2 hours fixing because I made this hideous error, and I can't really do editing very well. I'm just like crippled, okay? You see, I use all these words on myself. Crippled, retarded, dyslexic, backwards, just something's holding me back, but it doesn't stop me. That's the key. Well, you may be worried. I wouldn't blame you if you were. This guy's he's teaching me numbers, but I can't add, because anybody can add. In fact, that's the point. Let's go on. But my throat gets dry these days. By the way, let's get a good look at my eyes. This is why I wear these glasses. Yeah, does that look... It's allergies. But you would think, oh, he's on heroin, or, he's strung out on some kind of speed, he doesn't get enough sleep, or he's stoned. You never know with me. And that's why beatniks wore dark glasses, because they were stoned, and I am from San Francisco, so guess. There's more than one reason why my eyes look better with shades over them. I think it looks great. But you gotta wonder, how many scientists, when they give a lecture, if your professor walked in, a tie, that's nice, but then you still have to ask, what? Nobody wears shades to give a lecture. Well, unless you just came from the ophthalmologist, which you don't know. So don't ever jump to conclusions. Assume the person is rational. I mean, unless they're wearing a dunce cap with a propeller on top. People do things to get attention, too, by the way, and I might be doing that. Because they need peer review. But if so, I want it to be from Dr. Sabine Hassenfelder, with her husband present, and their 2 kids. Because I don't want anyone to think, yeah, I'm a chicken snatcher, or whatever they call it, because she's 20 years younger than I am, anyway, so that'd be like cradle robbing. Plus she's married, happily married, and has 2 kids. Well, I think I'd be worse than a rapist. So don't ever think that. But that's the one that I want to review, because she's nice looking. No, it's not the reason. The reason is because she is the foremost physicist on Earth right now. You know how I know that? I can get away... Oh, in a pub? I'd stand up. Yeah, we'll brawl. Dr. Sabine, don't you dare contradict me on this. Bloody nose out in the alley. We're duking it out. Dr. Sabine is my heroine. Now everyone's looking. He just said heroine twice. That guy with the dark glasses who calls himself the professor, he keeps saying heroine. Well, I'm talking about Dr. Sabine. And he's in love with a married woman. No! But I would like her to review my discovery, which is what again? Well, it has to do with these numbers. So let me show you something else. Well, first of all, let me show you what this is. 0 is the beginning of the linear number system. Just so you know, what I discovered is the spherical number system, which doesn't begin at 0, it begins at 1. And if you know anything about the universe, uni means 1. It doesn't mean 0. Like the zero verse. I don't know if anyone's ever thought of that. You know, you have multiverse. That's, by the way, an artifact of linear algebra confusion. Why do I keep saying that? Because the universe is spherical. I mean, if you had to sum up in one sentence, what did you learn in physics for 4 years or the 16 years? Or you just heard of it? What do you know about physics? You can answer really mightily well by finishing this lecture and getting on with it. So, 0 is the beginning of the linear number system. Now, John, that is John Horton Conway, who died of the COVID virus 3 years ago, my hero, because he gave me the key. That's what I'm going to show you here. This first tier with -1 and 1, which I just described to you as having a 180-degree valence on the line. Well, that 180-degree valence, it's two opposite directions. That's how we say it. We have X, or whatever you call your line, with an index of 1 so you can do spatial separation. That's science. That's it right there. Draw that line and start measuring distance. Spatial distance. Right? Any graph you ever see, it has time off on the side. Or it draws it on the y-axis. But what we're measuring is not time. We're always measuring distance. Always measuring distance. But could we measure time? That's what we're getting to. Because Einstein said you're going to have to now. Because every time you measure distance, you're measuring time. That's called relativity. It means it changed our whole interpretation of the line. Because he's basically saying it's not linear. That's what he said. It is not interpreted that way because all we have is linear numbers. But you see, that's because we use the line. But if you use the line to start your numbers, which we did, and it's miraculous on Earth, that 0 will come back to haunt you. You'll be able to do anything you want on Earth, and that's the miracle of calculus. That's why there are thousands of books written on calculus, tens of thousands of pages that you have to wade through, or you won't make the maximum amount of money. There's a reason for that. Of course I put it down. Because I'm studying heaven, then I have to, because heaven is higher. But it's a Pyrrhic victory, because I myself, I'd be a hypocrite. I kind of am. Because we're so heavenly minded, we're no longer of any earthly good. There's a lot of truth in that. If you're after the understanding of the actual, real reality, well, that's obviously going to be in heaven. Yes and no. Because you didn't say enough. Because when you go out into heaven, right, with your telescope, you're looking at, well, have you seen the edge yet? No. No. Will you ever? No. Well, that's pretty harsh. Because now you have a problem. There's no number for that. There's no number for what you can't see. That's called the outer product infinity. But you see it's outer. What about inner? You have heard of the infinitesimal, the world's smallest number, the universe's smallest number. Well, Max Planck, and we're getting to Max in a moment here, found out there actually is such a thing. Well, that contradicts infinity going in. What about going out? Well, we haven't found the reciprocal of the quantum yet. Well, actually, I did. So here's where you find it. You start at 0. That's called the Archimedean balance point of the space. The space is a geometric space. In this case, for a number system, it must be a geometric object. I'm able to state that retroactively because the sphere is the number 1. The point is the number 0. For the center, that's for the center. The center of the linear system is a point. And because you're using it for linear separation, that is the line, then that 0 means 0 distance. And that's a hole in your system. Your numbers will not be able to handle 0 if you try to apply multiplication. Multiply is not a linear operator. We're getting to that, and this is going to go an hour. For these lectures, this is intensive, and I am trying to keep it lighthearted, but this is going to get brutally intense. It's going to break your mind, or your balls, or your ass. It's going to break your bones. It's going to break you. No, science it fails when it does that. So it's very important to start slowly here. The center is 0 because the metric is 1. In order to have the metric of 1, which is defined as linear separation in space, it's a spatial concept. Okay? You know that everything changed with Albert Einstein, and now we need a number for time. Do we have it yet? No. Well, what's holding things up? Nobody knows how to begin to get time as a number. But if you begin at 0, it's impossible. You'll never get time as a number if you begin at 0. But if you begin at 1, you might wonder if there's a number system attached to that center. What if 1 were the center, not 0? 0 is the center of linear space. You're looking at it right there, okay? Right over there. You're looking right down there at the bottom. This is a tree that grows upward. It's the leaves of the tree. This also can be inverted, and in fact, let's show you that. Oh, but before we do, I want you to notice that this is day 0. And if you think I'm making that up, I'm not. That's what John Horton Conway says about his own system. That 0 is born on day 0. But the genius of John Horton Conway was how he defined 0. He defined it as a 2-component number. And all of these numbers are 2-component numbers on a definitional basis. These are the definitions of all the numbers. All the numbers. Even the impossibly infinite ones. They're all in here. All of the infinities, I should say linear, all of the linear infinities are in here. Where you see omega, and let me show you where that is. I don't have a pointer, and there's no way to highlight this because it's an image. But if you start at 0 at the bottom and go up, you get the valent 1. It's 1 with a charge. That's plus and minus, yeah. Well, I'm just going to call it charge. I'm allowed to make up a word if I want to. You think of it as plus and minus. Well, I'm just going to say that that's charge. The reason I want to say that is because that's one new number. This is one number. It's the number 1, but it's split. It's split on 0. And that's the definition of the number line. Not quite. We got to keep going. We'll have to reach the end of this parabola going up in order to get the entire definition of every single number in the number system. This is the linear number system. How do I know that? Because that is a 0. That's the definition of the balance point of the space numerically. But now you have to add something to that. And add is a pun. You have to add the operator. To get from 0 to 1, you need an operator. That operator is called add. And because this number has a negative in front of it, you do not need subtraction. And that was taught to us in school, but it's easily forgotten. There is no such operator as subtract. It's illogical. It is consistent, however, and it's convenient. And so we do use subtract. But we shouldn't. Logically, we should not. Every operation in linear space is add. And that's it. There is no multiply. Why not? Because it's not closed on the line. Only add is. And there's only one other operator besides add. I discovered that. So let's go on to day 1. Day 0, a 2-component 0 was invented in the genius mind of John Conway, for which he deserves 3 Nobel Prizes, in my humble opinion. But he won't get any because he's dead. The last of the polymaths. And the only polymath before John Conway that science can remember was Joseph Bošković. That is Ruđer. Josip Bošković. After Bošković, it's about 250 years, and then we got John Conway. They are both dead, but I'm not. So on day 1, we get the valent 1. On day 2, we get the quantum numbers. I discovered that. Every single number on this line is part of one number. Because in order to use 0 correctly, you need 1. And I'm going to teach you what those two numbers are called in the geometric definition of linear space. The 0 is the Archimedean balance point of the line. That means it's the Archimedean balance point of the number system of the line. That's 0. 1 is the index. It's not the Archimedean balance point of linear space. It's the index of linear space, which has to be defined on something physical. Physical. That is spatial, linear separation. That has another name. Distance. It's also called length. And those are synonymous. Distance, length, and the correct name for it, linear spatial separation. That's critical that you memorize that. That is the definition of the index of linear space, and it has a name because it has a number. It's 1, but that is an incomplete definition. Why? Because it's a distance between 2 points. So when you say 1, you haven't said anything physical. until you complete your sentence, it's 0 to 1. That's the distance. It's from 0 to 1. That is called the metric. So now you've learned 3 new words. Big day for us here. 0 is the Archimedean balance point of linear space. 1 is the index of linear space. And 0 to 1 is the operator add that defines the metric of linear space. Now we go to day 2. This was day 0 for 0, which was born as 0, 0. On day 2, we get 1, 1. I'm sorry, well, if this is day 0, this is day 1. And that's convenient, you'll see, because on day 0, we define the Archimedean balance point. On day 2, we define the metric and the polarity, also called the valence of the metric. This is the valence of the metric is 180 degrees. On day 2 are the quantum numbers. On day 0, you have 0, 0. On day 1, you have 1, 1 with valence. On day 2, you have 2, 2 with a different valence. And that's the difference. Instead of starting here at 0, you start at 1. And that eliminates the negative numbers. So what are you measuring if you begin with 1? You're measuring spherical separation in space-time. That's the definition of what a quantum number is. The first quantum number is 2 1/2. That is one number. In the same sense that 1 negative 1 is the same number based on a center point of 0, 2 1/2 is one number based on a center surface of 1. And that surface is not a line. It's a sphere. I proved that. What I want you to see now is what happens when you go from 0 to 1. You know what that is. Now you know what happens when you go from 1 to 2 and what happened to the negative numbers. We just switched data type. We're no longer, when we start at 1, instead of 0, first of all, we left 0 behind. And 1 is the smallest number. That is the number of the universe. And Max Planck and Albert Einstein teamed up, although they actually didn't understand precisely what the other one discovered. I synthesized their 2 discoveries, and it turns out it has a geometric and mathematic significance that changes the face of science. You don't begin at 0 to do mathematics the way the universe does it. You begin at 1, and now you've lost the line. You can't lose the line, and that's why it took so hard. It was so hard to discover this. It was very hard for me. I spent months working on this problem, and it went to dream time. That happens. And then it wasn't precisely in one day, but you notice that you have a flash that's different than the other flashes. And you pursue that one. That's my testimony to how this works for a discovery of the order of this. This is the original number system of the universe, from which the zero-based system is a derivative. It's the linear derivative of the spherical number system. it's on John's graph. All you do is you change the base of the tree from 0, which splits to 1, -1. You choose 1 and begin there and throw out the other half. But now you need a 2-component number. That's the rub. You now need 2 numbers to make 1 number. The genius of this diagram is it shows that the linear number system is embedded inside. Actually, it shows the opposite. But that's because we're seeing it inside out. Actually, the number 1 is the convergence of 2 1/2 on a harmonic. So you actually read this the other way. It should be a root tree system, not a leaf tree system. This is a leaf tree system, giving the impression that the 1 base system is derived from 0. It's not. The 0 base system is derived from the 1 base system. And it has a flip inverse of -1. That's an illusion, but it has a deep significance which I'm going to teach you in the months ahead. This is the theoretic and geometric basis of a brand new way of computation that is more consistent with reality than the linear number system itself. But the only reason that that's true is because it is a linear number system. But the linear numbers are combined into a new form of number called proportional number, and that's the meaning of 1/2. You see, that's the beginning of the dyadic fractions. The dyadic numbers are, first of all the counting numbers, but the dyadics include fractions, but they only include fractions that have as the denominator a power of 2. So what is 2 to the 0th power? That's 1. That is deep. I hope you're enjoying this. We're coming up on 1 hour. I have about 10 other things I want to discuss with you, but I knew this would happen. It's very important to see the sequence that I just showed you. I didn't realize that's what I was going to do tonight. But 0 is the basis of the linear number system, and that's add. But 1 is not add. 1 makes a sphere, not a line. And the sphere does not have add. It has multiply. But it's actually not multiply because multiply has an inverse. And so the right way to say that would be multiply divide. But that too is incorrect because it can be simplified to a term that describes both operations at once. And that is called proportionality. Every time you see a fraction, like the speed of light, that is a 2-component number. That's why we write them as fractions. They're called rational when the 2 numbers being used are whole numbers. Beginning at 1, there is no 0. That is miraculous because that alone will solve the calculus derivative integral system. We're now in integral space. These are the rational numbers. But you see, it's more specific than the rational numbers. Well, actually, where's 1/3? The dyadic rationals include all of the counting numbers, but also include the binary fractions. Because it splits on 2, that 1/2, 1/4, 1/8, that's why you see it going down here. From 1/2 it goes to 1/4, from 1/4 it goes to 1/8. This number is the infinitesimal. It's 1 over infinity. I discovered the significance of that number. This number, 2, goes off to another infinity. This number omega is integral infinity. This number 1 over omega is also called epsilon, and it is the integral infinity. These are numbers. They're rational numbers. Well, it's a bit... no, they're not rational numbers. They're very special numbers. I discovered how they work together. You cannot think of the infinitesimal and the integral as being separate. And in fact, in spherical numbers, these two numbers go together. You know why? It's because all spherical numbers are 1. 2 times 1/2 is 1. 4 times 1/4 is 1. Every time you do that, you're computing time and space together to get light speed. And the lowest number that can do that, that can define light speed, is 2 1/2. And that's called the quantum number. It's the lowest number on integral light speed that can be measured. It's the jump from light speed to half light speed, or double light speed. But actually it splits so that you don't get double light speed. You can't ever get double light speed, but you can double the distance, or you could double the time. But when you double the distance, you contract the other number, because it has to multiply to 1. So when you make the quantum jump from 1 to 2, there's a reciprocal and equally opposite reaction. On the quantum jump from 1 to 2, to get the first atomic shell, that's called the quantum jump. That's a jump from 1, which is the spherical surface, to the quantum shell, that's 2, with nothing in between. But as that happens, that's in space, but it's spherical space. The reciprocal is a contraction of the number on the sphere, because there's no inside of the sphere. You know why? That's epsilon. And epsilon is imaginary. It can never be used, it can never be touched, and it takes the place of 0. It's purely imaginary, and therefore it bounds the system. And the same is true of omega. That is the edge of the universe, is omega in spherical space. But when you say that, you haven't said everything. Omega only exists to the proportion that epsilon exists. And that means that the universe has an imaginary center mathematically. That's the definition of the universal number system. It has no center unless you know what it is. It does not have a point at all. There's no point, because the definition of the point is 0. The universe does not have 0. It has a force relation on unity that balances on angular momentum, and that's where we're going to go in the next lecture. That's a little over an hour, but I'm going to edit this. I might not. I might just publish this as it is. I hope you've enjoyed this. We had plenty more to show you. I just want to give you some teasers here to show you. We're going to talk about, these are the dyadic rationals. You see it down here at the bottom. And the dyadic rationals are part of this article in Wikipedia, the dyadic rational. The diagram I showed you was this thing here. Just clicking on that. The dyadics, these are the dyadic rational fractions. The dyadics include all the counting numbers. They're the whole numbers plus these. These are called the representable numbers, although there's more technical detail. It's going to show you here. You might have asked, where is 1/3? That's not a dyadic. 1/3 is the first fraction in whole numbers that is not dyadic. Where do you find that? Well, you find it, I can't point it, but I'll show it to you now and then we're going to close this. You go 0 to 1, you go up this right side, go up with me, then you go 1 to 2, right? Well, we took a wrong turn, go back to 1, and go down to 1/2 to the left, then keep going 1/4, then to 1/8, and then you get to 1 over omega. That's epsilon. That is the calculus infinitesimal of spherical space and circular space. It depends, but this one is linear space. That is the linear omega. But as soon as you get to linear omega, you've gone too far. Go back to 1/8, go back to 1/4, now go the other way, and you get a 3. Because 1/4, when you go by powers, we've gone from 1 over 1, 1 over 2, 1 over 4, 1 over 8, but you don't have to go 1 over 8, that's less. 1 over, you could go 3/8. That's where 3 enters in. And where that reaches the same level as the infinitesimal, you have 1/3, which is a repeating decimal. We're gonna, numbers are fascinating, but I hope you realize this is much better than anything that Martin Gardner ever published. This is the number system that the universe uses. This number system has never even been tried. All right, I'm going to show you more of that in the months ahead. Let's just go back here. There is 0, 1. This is the tree upside down. And I'd like to show you one more thing before we close completely. Let me get over there. This I wanted you to see. We'll cover this in the next lecture. This is called the Planck constant. The Planck constant is the lowest counting number in the universe. But it has several forms, and it's important to know what it's saying because you can tell I have something here that shows 3 different Planck constants. There's H, which is the linear quantum. It's the Planck constant, the quantum of action. The next one going up in the image here, you'll see, this one, the second one, let's see if I can highlight that. There we go. That's the reduced Planck constant called h bar. And that's the reduced quantum. What's the definition of the reduced quantum? It's h over tau. And tau is the circular surface number. It's 2 pi. That's what tau is. And h bar is h over 2 pi. Well, that should be tau. And that's because there's another one. Because that's the circular quantum. But is there a spherical quantum? I discovered it. The spherical quantum, which I have, I'm going to highlight that here. You see that? That's the one at the top that's labeled H2 bar with 2 slashes through the H. That's H over 2 tau. 2 tau is the surface number of the sphere. What I've done is inverted that to make this, the universe did that for me. The surface of the sphere has a value already. It's 1. Which means that we have some very interesting stuff ahead, don't we? This is completely explanatory of all the paradoxes, both in astrophysics, believe it or not, and of course in quantum mechanics. That'll be in the upcoming lectures. And we're angling toward getting back to my 3rd presentation in 3 months on the flight of the photon, which demonstrates the usefulness of spherical geometry. because it solves the quantum paradox instantly. And it just takes a while to get used to. But the more you get used to it, the more you have evolved. This is actual evolution. Evolution occurs only in science. To the degree that you learn geometry, you're approaching wisdom. But geometry has a specific purpose. And there are two geometries, as you well know now. There's linear geometry, that's for Earth. For heaven is spherical geometry. Everything in heaven is spherical. And everything at the center of heaven, which is quantum space, those are spheres. Everything is spherical. I've proved that the universe is spherical, and it gets rid of the calculus. And we'll use nothing but positive rational numbers from now on, never with division by zero, never any problem with infinity. Infinity bounds spherical space. That solves the Kurt-Gödel problem. And also we're going to solve the Heisenberg uncertainty principle. But it has a surprising answer, as you might expect. It has to do with the relationship between space and time. This is Anagalactic. On the last day of February, now approaching, we're 1/4 of an hour from March, because this is not a leap year. We'll be right back. Stay tuned for the secrets of the universe. This actually is the secret in terms of mathematics, not quite as important as geometry. The geometry of the sphere with its number system that solves every problem on the list. We'll be right back.